My name's Bob Harlow. I'm Professor Jason Harlow's identical twin brother. This is the physics building. Today, I'm going to talk to you about falling objects.
Unfortunately, that was the last known footage of my dear old brother Bob. But don't worry, I'm here and I can teach you today about falling objects. So this is section 2.7 on page 89 of your PDF, or 71 paper version. And this is about gravity. The most remarkable and unexpected fact about falling objects is that if air resistance and friction are negligible, then all objects fall towards the center of the Earth with the same constant acceleration, independent of their mass. This experimentally determined fact is unexpected because we are so accustomed to the effects of air resistance and friction that we expect lighter objects to fall slower than heavier ones. Here they show an experiment that was done on the moon where an astronaut dropped a hammer and a feather at the same time, and they fell with the same acceleration. And the reason they fall with the same acceleration is because they are in a vacuum, meaning that there is no air resistance that slows down the feather. So air resistance acting on a hammer is pretty low here on Earth, but it's a lot compared to the weight of a feather, and so feathers don't fall at this regular rate. But they would if you took away all the air. So here on Earth, the acceleration due to gravity for objects that are not affected much by air resistance is 9.80 meters per second squared. So if it was a vacuum, everything would fall at this rate. But if there is air, then really heavy or very condensed objects will fall with approximately with this rate, maybe a little less. So once you know that, there are these same kinematics equations, which are the equations of constant acceleration, at least 3 of them, but they've rewritten them here with, instead of x, they've written y. Okay, so y here, I guess would mean vertically up. So plus y is in the up direction. Then the acceleration in that direction is negative g. So instead of a, like plus 1/2 at squared, you put minus 1/2 gt squared. And then this is the y component of the velocity, and speed squared there. So those are handy equations. There's a couple of good examples. Here's a rock thrown upward. So I encourage you to work through that example. Another example of a rock that is thrown downward, so you can have a negative initial velocity and a negative acceleration. And here's an example I want to pause on, example 2.16, finding g from data on a falling object, because this kind of shows really what happens here. So here is a rock, or sorry, metal ball, which has very negligible air resistance on it, and is released from rest, meaning that someone lets it go without throwing it up or throwing it down, but just releases it gently from rest. So, and you can define, I guess, your initial y position as being 0. So in that case, initial time is 0, initial y is 0, and if it's released from rest, the initial v, or velocity, is 0. So then, 0.1 seconds later, for every 0.1 seconds, the velocity changes. There's a delta v of negative 0.98, because that's 9.8 meters per second squared times 0.1 seconds. You get negative 0.98 meters per second. So, and that just keeps on happening. Every tick of the clock of 0.1 seconds gives it an additional delta v of negative 0.98. It's almost 1, right? So, or almost 0.1. So, sorry. Almost 1, so negative 1, negative 2, negative 3, negative 4, negative 5 meters per second. So that's the speed, but the distance between these positions, if you were to take like a snapshot at individual moments, that increases. So originally, the sort of average speed is less than 0.1, so it only goes a tiny little bit. But as the average speed between moments gets bigger, the distance gets bigger and bigger. And so if you were to graph that, you actually get a curved graph of position position on the vertical axis here downwards versus time for the falling sphere. But you get a straight line for velocity versus time, and you just get no line at all, just a negative 9.8 constant for acceleration versus time. And that leads us to section 2.8, graphical analysis of one-dimensional motion. I encourage you to look at this PHET exploration. So if we click on that, it takes us to this equation grapher. So basically you can select the different constants in this equation. Y is the vertical axis equals ax squared plus bx plus c. This is called the quadratic equation because it's got these x to the power of 2 is the largest factor of x. So c is just the constant. If a and b are 0, then this just brings it up and down. B is the slope. So actually c is sometimes called the y-intercept because it turns out to be the position, the y position at x equals 0. And then a is that quadratic term. So this is what gives it its curviness. So sometimes, I don't know, you could look at something that was thrown with an initial position of 3.6. Let's say y here is, I don't know, vertical position, and x is now time. If you make x time, then something that's thrown with an initial position of 3.6 upwards with 1.4 meters per second, and then accelerates downwards. Oh, I can't get to negative 9.8 on this thing, but you get it. It would be, it would look something like that. It would go up and down a curved path. So you can play with that. So the basic idea here, so again, the equation of a straight line is, sometimes you know, y equals mx plus b, where m is the slope and b is the y-intercept. We're going to kind of apply that equation to our equations of constant acceleration. So the first one we had was x equals x0 plus vt, or v average times t. So that actually is that equation. It's just that instead of y, now we have x, and instead of x, we have t. And instead of slope, we have that average velocity, and instead of the y-intercept, which is, I guess, the x-intercept, you have the initial position. And then there's graphs of motion when a is constant, but a does not equal 0. These are these curved lines. You can actually make a plot of v versus time, and here is that equation. It's another one of our equations of constant acceleration. V equals v sub 0 plus a times t. So in this case, you've got v on the vertical axis and t on the x-axis, and a, the acceleration, is the slope, and the initial speed is your y-intercept there. So if you had a graph of velocity versus time, you could get the acceleration just by dividing delta v divided by delta t, so rise over run there. And that's it for chapter 2. Actually, there's a glossary with some good terms. There's a summary which goes on to a couple of pages of every section, including falling objects and graphical analysis. And then there are a bunch of conceptual questions followed by problems, and I'll give you some problems and exercises, and I'll give you some end of chapter items to complete as part of your problem set. Okay, and next time video we're going to get into chapter 3. Bye for now.